In this video, I will discuss splitting of d orbitals in various complexes. In this, we will be discussing shapes of d orbitals, splitting of d orbitals in octahedral complex, splitting of d orbitals in tetrahedral complex, and splitting of d orbitals in square planar complex. Before going into details of splitting of d orbitals in different environments, we need to know their orientation along x, y, and z axes. We know that there are 5 types of d orbitals: dxy, dyz, dzx, dz square, and dx square minus y square. Among these orbitals, dxy, dyz, and dxz are lying between the axes, while dz square and dx square minus y square are lying along the axis. Splitting of d orbitals in octahedral complex. The general structure of an octahedral metal complex can be represented by this formula. These are the 3 axes x, y, and z. When the metal is free, all the 5 d orbitals have the same energy and are termed as degenerate. When the ligand approaches towards the metal ion for the formation of metal complex, the energy of d orbitals is raised due to repulsion interaction between the negative charge or negative pole of ligand with electrons on the metal ion. If the ligand environment is spherical, which is a hypothetical case, the energy of 5 d orbitals will be raised to the same extent, but they will still remain degenerate. In an octahedral ligand environment, ligand approach the metal along x, y, and z axis. We know that dx square minus y square and dz square orbitals are lying along the axis. So, due to higher repulsive interaction, their energy will be higher than the energy of d orbitals in spherical field. dxy, dyz, and dxz are lying between the axes. So, due to lesser repulsive interaction and to conserve energy, their energy will be less than the energy of d orbitals in spherical field. The set of dx square minus y square and dz square orbital is called Eg, while the set of dxy, dyz, and dxz orbitals is called T2g. The difference between the energy of T2g and Eg is denoted by delta O, where O stands for octahedral. This value can also be represented as 10 dq. The difference between the energy of Eg and the energy of d orbitals in spherical field is plus 0.6 delta O or plus 6 dq. And the energy difference between the T2g and the energy of d orbitals in the spherical field is minus 0.4 delta O or minus 4 dq. Splitting of d orbitals in tetrahedral complex. A regular tetrahedron is related to a cube. The central metal of a tetrahedral complex is at the center of the cube, and the 4 ligands occupy alternate corners of the cube. These are x, y, and z axes pointing to the center of the faces of the cube. When the metal is free, all the 5 d orbitals have the same energy and are termed as degenerate. If the ligand environment is spherical, All these 5 d orbitals will increase their energy with equal amount. That means they will still remain as degenerate orbitals. We know that dx square minus y square and dz square orbitals are lying directly along the axis, whereas dxz, dyz, and dxy orbitals are lying in between the axes. In tetrahedral ligand environment, none of the 5 orbitals are directly pointed towards the ligand, but dxz, dyz, and dxy orbitals are nearer to the direction of ligand than the other two orbitals, that means dx square minus y square and dz square orbitals. So, the energy of dxz, dyz, and dxy will become higher, and dx square minus y square and dz square becomes less energetic than the spherical environment. Thus, the d orbital splitting in tetrahedral environment is just opposite than the d orbital splitting in octahedral environment. The set of dx square minus y square and dz square orbitals is called E, while the set of dxy, dyz, and dxz orbitals is called T2. The G term will not come here due to lack of center of symmetry. The difference between T2 and E is denoted by delta T, where T stands for tetrahedral. The difference between dxz, dyz, and dxy orbitals energy level to the barycenter is 0.4 delta T, whereas the difference between dx square minus y square and dz square to the barycenter is minus 0.6 delta T. The relationship between delta O and delta T is as following. Delta T is equal to 4 by 9 delta O. The lesser amount of splitting in tetrahedral system is due to the two reasons. The first reason is that the number of ligands is less in tetrahedral system than in octahedral system. The second reason is that the ligand's approach in tetrahedral system is not directly along the axis. Splitting of d orbitals in square planar complex. Suppose we have an octahedral complex. If we remove the two ligands from z axis, it would result a square planar complex. The d orbital splitting diagram for the square planar complex can thus be derived from d orbital splitting of an octahedral complex. This is the d orbital splitting of an octahedral complex. As ligand moves away from z-axis, d orbitals having z component will fall in energy. The dz square orbital falls the most, as its electrons are concentrated in the lobe along z-axis. The xz and yz orbitals drop their energy, but not as much as dz square. The x square minus y square and dxy orbitals increase in energy because the ligands in square planar complex move a little closer to the metal. This is the d orbital splitting pattern in square planar complex. The energy of dx square minus y square, dxy, dz square, and dxz and dyz respectively are 1.23 delta O, 0.23 delta O, minus 0.43 delta O, and minus 0.51 delta O. The difference between the energy of dx square minus y square and the xy orbital is equal to delta O.